What if the space between you and the most distant galaxy is not really there in the way you think it is? What if distance, the thing that seems to separate every star, every planet, every atom, every person, is not a fundamental ingredient of reality at all? Imagine that the universe is not a vast container filled with objects scattered across unimaginable emptiness, but something stranger, a network of relationships from which the very idea of far away emerges. If that is true, then the deepest mystery of space is not how large the universe is. It is why anything appears separated in the first place. Right now, distance feels undeniable. Your hand is a certain distance from your face. Earth is roughly 8 light minutes from the sun. The nearest star system is more than 4 light years away. The Andromeda Galaxy is about 2.5 million light years from us. These numbers describe real measurements, and no serious physicist disputes their usefulness. But physics has repeatedly taught us that something can be measurable, reliable, and essential without being fundamental. Temperature is real, but a single atom does not possess temperature in the ordinary thermodynamic sense. Temperature emerges from the collective behavior of enormous numbers of particles. Sound is real, but there is no tiny object called sound hidden inside the air. It emerges from coordinated vibrations. A wave exists, yet the water molecules themselves mostly move locally, while the pattern travels across the surface. Distance may belong to the same strange category. To understand how radical that possibility is, we have to return to a time when space seemed much simpler. For Isaac Newton, space was essentially an invisible stage. Objects moved through it. Planets crossed it. Light traveled across it. Space itself did not need to participate in the drama. It was simply there, extending endlessly in all directions, providing a universal framework in which every event could be assigned a location. If 2 objects were separated by 1 meter, that meter seemed like an objective feature of reality. Every observer should agree that the separation existed, regardless of how they were moving. Then Albert Einstein dismantled that picture. Special relativity revealed that observers moving relative to one another can disagree about lengths. A ruler moving past you can be measured as shorter along its direction of motion. 2 events that appear simultaneous to one observer may not be simultaneous to another. Space and time could no longer be treated as independent absolutes. This did not mean measurement became arbitrary. Quite the opposite. Einstein replaced the old absolutes with a deeper structure, spacetime. Within spacetime, certain quantities remain invariant even when observers disagree about distances and durations separately. The lesson was unsettling. Space was not what human intuition had assumed. And then Einstein went further. In general relativity, gravity is not simply a force pulling objects across a passive arena. Matter and energy influence the geometry of spacetime itself. Distances depend on that geometry. Put a massive object into the universe and spacetime changes. The paths followed by planets, photons, and falling bodies change with it. Near a black hole, the geometry becomes so extreme that ordinary intuitions about distance can fail dramatically. Imagine trying to ask a simple question: how far is a point outside a black hole from another point closer to the horizon? The answer depends on exactly what you mean by distance. Along which path, measured by whom? At what moment? In which coordinate system? Coordinates can make a horizon appear infinitely distant in one description and perfectly reachable in another. The physics remains consistent, but the naive idea that distance is simply a fixed number written into the universe begins to dissolve. That was already strange. Quantum mechanics made the problem far stranger. In the 1930s, Einstein, Boris Podolsky, and Nathan Rosen studied a feature of quantum theory that seemed almost impossible to reconcile with any ordinary picture of separated objects. 2 quantum systems could become entangled so that their measurable properties were correlated in ways that could not be explained by assigning each system its own independent local state. Measure one particle here, and the results remain correlated with measurements performed on the other particle far away. Einstein famously objected to what he saw as an unacceptable kind of non-locality. Later experiments testing Bell inequalities showed something profound. Nature cannot be explained by local hidden variables of the simple kind Einstein hoped might restore a classical picture. Entanglement does not allow faster-than-light communication. You cannot use it to send a message instantly across the galaxy. Relativity survives. but something about separateness has changed. Two objects can be distant in ordinary space while sharing a single quantum description that cannot be decomposed into independent pieces. That raises a dangerous question. What if spatial separation is not the deepest form of separation? This is where physicists such as Leonard Susskind entered a story that would eventually challenge the meaning of space itself. Susskind spent decades thinking about one of the most unforgiving objects in theoretical physics, the black hole. Black holes appear to hide information, throw something into one, and according to classical general relativity, it disappears beyond the event horizon. But quantum mechanics is built around the idea that information contained in a quantum state cannot simply be destroyed. Stephen Hawking complicated the problem in the 1970s when he discovered that black holes are not completely black. Quantum effects cause them to emit thermal radiation and slowly evaporate. If the radiation were perfectly thermal and carried no information about what formed the black hole or fell into it, then after the black hole vanished, information would appear to be permanently lost. For Susskind, Gerard Hooft, and others, that possibility was intolerable. If quantum mechanics was correct, the information had to survive somehow. The argument pushed physicists toward an astonishing idea. Perhaps everything that happens inside a region of space can, in some sense, be described by information encoded on its boundary. The idea became known as the holographic principle. The name comes from ordinary holograms, where information stored on a two-dimensional surface can produce the appearance of a three-dimensional image. But in quantum gravity, the claim is vastly more profound. It suggests that the number of fundamental degrees of freedom inside a volume may scale not with the volume itself, but with the area of a surrounding surface. That immediately changes the way we think about space. If a three-dimensional region can be fully represented by information living on a lower dimensional boundary, then perhaps the interior spatial dimension is not fundamental. Perhaps it emerges. In 1997, Juan Maldacena gave physicists the most concrete example yet of this possibility. His ADS-CFT correspondence proposed a mathematical equivalence between a theory containing gravity in a higher dimensional space-time and a quantum field theory without gravity living on its lower dimensional boundary. It was a revolution. The two descriptions appear radically different. In one, there is an extra dimension of space. Objects can move deeper into the gravitational interior. Distances exist within a curved space-time. In the other description, that extra dimension is absent from the fundamental formulation. Yet the theories can describe the same underlying physics. Think about what that means. A direction through space can appear in one description even though that direction does not exist as a fundamental coordinate in the other. An entire dimension can emerge. And if a dimension can emerge, perhaps distance within that dimension can emerge too. Susskind became one of the most influential champions of this holographic view. For him, black holes were not merely cosmic objects. They were laboratories exposing the hidden architecture of quantum gravity. But another mystery was growing. What creates the geometry of emergent space? The answer may involve entanglement. Imagine a collection of quantum systems. At first, imagine they are not entangled with one another at all. Their states are independent. There is no deep quantum connection linking them. Now gradually increase the entanglement. Mathematical work in holographic theories suggests that the amount and structure of quantum entanglement are intimately related to the geometry of the corresponding gravitational spacetime. In certain settings, reducing entanglement can make regions of spacetime effectively pull apart. Increasing the right pattern of entanglement can help connect the geometry. This is not a poetic metaphor. Within well-defined holographic models, equations relate entanglement entropy to geometric areas in the gravitational description. One of the crucial relationships was developed by Shinsei Ryu and Tadashi Takayanagi. In appropriate holographic systems, the entanglement entropy of a region in the boundary theory corresponds to the area of a particular minimal surface extending into the higher dimensional gravitational spacetime. Information and geometry are mathematically linked. Later work by physicists including Mark van Ramsdonk sharpened the idea that connected spacetime itself might be built from patterns of quantum entanglement. That is where the phrase, "distance isn't real," becomes both tempting and dangerous. Distance is certainly real at the level of the world we experience. If you are standing 10 meters from a wall, treating that distance as imaginary will not help you cross the room. The more accurate claim is subtler. Distance may not be fundamental. Just as temperature emerges from microscopic motion, spatial geometry may emerge from quantum information. And the evidence for this idea is strongest in special theoretical models, not yet as a proven description of our entire universe. Still, the implications are enormous. Suppose two regions look extremely far apart in emergent space. At the deeper quantum level, what determines that separation? Perhaps it is encoded by how strongly or weakly different degrees of freedom are entangled. Then near and far would not be primitive facts. They would describe the structure of information. This gives us a new kind of map. Not a map drawn with kilometers. A map drawn with correlations. Consider the internet. Two computers can sit on opposite sides of the same room but be separated by layers of network structure, security rules, and routing paths. Meanwhile, two machines thousands of miles apart might be tightly connected within a digital network. Physical distance and network distance are different. Now imagine that physical distance itself emerges from a deeper network. The analogy is imperfect, but it points toward the idea. At the fundamental level, nature may not begin with objects placed at positions inside space. It may begin with quantum degrees of freedom connected by relationships, and geometry may be the large-scale pattern those relationships create. This possibility becomes even stranger when black holes return to the story. In 2013, Juan Maldacena and Leonard Susskind proposed a provocative connection summarized by the phrase ER equals EPR. ER refers to Einstein-Rosen bridges, structures related to wormholes. EPR refers to Einstein-Podolsky-Rosen entanglement. Maldacena and Susskind suggested that certain kinds of entangled systems might be understood as connected by non-traversable wormholes in an appropriate gravitational description. This does not mean every pair of entangled particles contains a science fiction tunnel you can travel through. It does not mean entanglement permits instant transportation. The proposal is more abstract. It hints that entanglement and space-time connectivity may be two descriptions of something deeper. What appears as a quantum connection in one language could appear as geometric connection in another. Information on one side, geometry on the other. And suddenly the distinction between connected and close becomes difficult to define without asking which description of reality you are using. There is another clue hiding in the behavior of black holes. Black holes are extraordinarily efficient scramblers of information. Quantum information falling into one can become distributed among the black hole's degrees of freedom in a highly complex way. Susskind has emphasized the role of quantum complexity in thinking about black hole interiors. In some theoretical models, features of the interior may continue evolving long after the black hole appears to have settled down from the outside. This has led researchers to explore whether not only geometry, but the enormous interior structure associated with black holes may relate to the growth of quantum computational complexity. Again, these are active research ideas, not established facts about nature. But notice the pattern. Area becomes information. Geometry becomes entanglement. Interior growth becomes complexity. The objects that once seemed most purely geometric are repeatedly being translated into the language of quantum information. Perhaps space is telling us what it is made of, not smaller pieces of space. Relationships. That would explain why trying to discover the smallest possible chunk of distance may be asking the wrong question. Physicists often discuss the Planck length, about 10 to the minus 35 meters, because that scale naturally appears when quantum mechanics, gravity, and relativity are combined dimensionally. It is sometimes described as though it were a literal pixel size of the universe. That is not something established physics has proved. We do not yet know the correct quantum theory of gravity. The Planck scale tells us roughly where our familiar theories are expected to require a deeper description, but what that description looks like remains unknown. Maybe space-time becomes discrete. Maybe it emerges from strings. Maybe it arises from quantum networks. Maybe the entire concept of geometric distance ceases to make fundamental sense. String theory, the field with which Susskind has been deeply associated since its earliest development, already contains hints that ordinary geometry is not sacred. Different geometric setups can sometimes produce equivalent physics. Dualities can relate theories that appear to live on very different spaces. In certain circumstances, a universe compactified on a circle of one radius can be physically equivalent to a description involving a circle with an inverse radius, once stringy effects are properly included. This phenomenon, known as T-duality, challenges the intuitive idea that the size of space must always be an absolute fundamental fact. To a point particle, a large circle and a tiny circle look completely different. To strings, the distinction can blur, because strings can not only move through dimensions, but wind around them. Momentum modes and winding modes can trade roles. The geometry we see may depend on which description we use. And whenever physics gives us two mathematically equivalent descriptions that disagree about something we assumed was fundamental, history suggests we should become suspicious of that assumption. The same happened with electric and magnetic fields under changes of motion. It happened with particles and fields in quantum theory. It happened with space and time in relativity. Now it may be happening with geometry itself. There is a thought experiment that captures the unease. Imagine beings who live inside a universe where space is emergent from a deeper quantum system. These beings build rulers. They measure planets. They calculate the distances between stars. Their astronomy works perfectly. Eventually, they discover the microscopic theory beneath their world. And nowhere in its fundamental equations do they find the distances they have spent centuries measuring. Instead, they find quantum states, entanglement, operators, information. The geometry appears only when the microscopic system is viewed collectively. Would their distances have been illusions? No. A hurricane is not an illusion because no individual air molecule is a hurricane. A human body is not an illusion because individual atoms do not know they form a person. Emergent things can be completely real, but they are real in a different way. Their existence depends on organization. This distinction matters when we look at the universe on the largest scales. Cosmology describes an expanding universe. Distant galaxies are, on average, carried farther apart as the cosmic geometry evolves. The phrase expanding space is useful, but it can mislead us into imagining some invisible substance stretching between galaxies. General relativity is telling us that the metric, the structure determining space-time intervals, is changing. If geometry itself is emergent, then cosmic expansion may ultimately require an explanation in an even deeper language. What changes in the underlying quantum system when the universe expands? What does increasing cosmic distance correspond to microscopically? We do not yet know. And this is important because the best understood examples of holography involve spacetimes that differ from the expanding universe we actually inhabit. Extending holographic ideas to realistic cosmology remains one of theoretical physics' major challenges. The temptation is to jump ahead and declare that the universe has already been decoded. It has not. No experiment has demonstrated that everyday spatial distance is generated by entanglement in precisely the way some holographic models suggest. No complete experimentally verified theory of quantum gravity currently tells us what spacetime is made of, but the clues are difficult to ignore. Gravity knows about information. Black hole entropy scales with area. Holographic duality can make extra dimensions emerge. Entanglement maps onto geometry in powerful mathematical frameworks. String theory contains dualities in which apparently different geometries describe equivalent physics. And black holes repeatedly force us to reconsider what inside, outside, near, and far actually mean. Perhaps the most unsettling implication is not that faraway objects are secretly close. It is that closeness itself may require explanation. Look at the night sky. A photon from Andromeda may travel for millions of years before reaching your telescope. That journey is physically meaningful. The space-time separation is measurable. Nothing in emergent space-time ideas erases the voyage. But beneath the geometry through which that photon travels, there may be a description in which the basic ingredients are not arranged in space at all. Space may be what the ingredients collectively become. The same quantum reality could contain the seeds of distance without containing distance as a primitive concept. And if that is true, then the universe is not fundamentally a collection of things separated by empty space. It is something closer to an immense web of quantum relationships, whose large-scale pattern gives birth to the appearance of a world with locations. You, Earth, the Sun, the galactic center, a quasar 10 billion light-years away. Each occupies a place in the geometry we experience. But the deepest theory may ask a different question. Not, where are these things? But, how are the underlying pieces of reality related? Maybe that is the question quantum gravity has been pushing us toward all along. Because if space can emerge, then the distance between two objects is not the beginning of the story. It is the end result of something deeper. And somewhere beneath every meter, every light year, every impossible cosmic gulf may lie a structure in which the word distance has not yet acquired any meaning at all, which leaves one final mystery. If the universe does not fundamentally begin with space, then before reality becomes divided into here and there, before the cosmos creates the distinction between near and far, what does it mean for anything to be separate from anything else?